This is an electric motor that I built from scratch in my previous video. And this is an old road bike I got practically for free. And in this video I will be joining these two to make this, my very own from scratch e-bike. To that end, I started, naturally, by trying to remove the rear wheel of the bike, as I had to figure out how I was going to transmit the power from the motor into the rear wheel of the bike. It took me a moment to realize I hadn't opened up the rim brakes, but once I did, I could start brainstorming. I removed the cassette. After finally finding a tool capable of unlocking the cassette, I removed the cassette. Ah yes, that was definitely 40 Newton meters of torque on that. Based on the simulations done in the previous video, I knew that the motor would have to have about 4 or 5 to 1 mechanical reduction. Otherwise, the motor would not make enough torque to be useful. So I found this 58-tooth chainring to be the wheel sprocket, and this 12-tooth BMX freewheel to be the motor sprocket, giving me a reduction ratio of 4.83. I decided that the easiest and rigid enough way to attach the chainring to the wheel would be to use a disc brake rotor to couple the chainring to one of the sprockets on the cassette. Now, since I was going to use bolts to produce the coupling force, then I needed to thoroughly clean the cassette. In case you didn't know, the coupling strength from a nut and bolt coupling actually comes from the friction force of the two surfaces, not from the tension of the bolts. Next, I needed to disassemble the cassette to get at the individual sprockets, for which I had to drill out some rivets. By the way, don't be stupid like me. Don't wear gloves or loose clothing around power tools. Trust me, eventually it won't end well. I then 3D printed some forms to know exactly where to drill the required screw holes. I also realized that the disc brake rotor couldn't fit on the cassette spline without modification, so out came the hacksaw. And let me tell you, that was absolutely not a pleasant experience. But the result was satisfactory. So, I cleaned all the coupling surfaces with isopropyl alcohol and then used the nuts and bolts with threadlock to make the full motor sprocket assembly. The comically large chainring sprocket thing fit on the cassette spline very nicely, and at this point I could reassemble the whole cassette, though I did have to use the sprockets a bit out of order. And yes, coupling the motor this way does mean I lose access to a few of the low speed gears, but I expected the motor to be able to offset the lack of these gears. Next, I reinstalled the rear wheel, and since I didn't know the condition of the drive chain, then I also decided to replace that. Next, I needed to figure out how to couple the motor to the bike frame. So I fired up Blender and designed these completely bespoke motor clamps. They are made of 3D printed PETG with some inserts for the clamping screws to screw into. But I also decided that I would produce some steel strips for some extra rigidity. Unfortunately, the front shifter and the front shifter cable got in the way of the clamps, so I had to remove it. This does mean that I have to manually shift the chain rings if I want to do so. After that, I just put the brackets where they belonged and plopped the motor into the brackets, and then fixed them with some beefy M8 bolts. Then it was time to install the freewheel on the motor. Now this is a bit complicated, but the freewheel connects to this coupler. Then inside this coupler there is an expansion sleeve, which in turn couples the whole thing to the motor shaft. Why go for a freewheel at all? Well, I simply wanted to be able to pedal the bike without rotating the motor. Regardless, while a little bit overcomplicated, this coupling mechanism seemed to work. I then added the Flipski 75100 motor controller that I had found worked great with my motor. Next it was time to add in the motor chain. However, at this point I realized that the slack in the chain would impact the bike frame. No bueno. So I had to figure out some kind of a tensioner. I acquired a cheap bike chain tensioner, but I had to modify it extensively, along with some 3D printed parts to get something that worked. And then I could finally join the motor chain. At this point, the only thing left to figure out was the battery. Now, some bold DIYers make their own batteries, but I'm not bold. At the same time, I'm also not sure I want to spend 200 euros or more on a proper e-bike battery. Yeah, that's right. I decided I would use some cheap power tool batteries. A friend of mine has done this before and it worked for them, so I figured it would work for me too. So I 3D printed my friend's designed battery holder and added the necessary connections. 2 parallel sets of 2 batteries in series should do the trick. At this point, the last thing I had to do was to run the motor detection through the VESC tool. Make sure the motor spins in the correct direction, and then calibrate the throttle. At which point, the e-bike was done. Time for a test ride. I plugged in the battery and I somehow immediately managed to break the motor chain tensioner. Minor setback. It was a bad design anyways. Remember the front shifter I removed earlier? Well, I modified that to make a more robust tensioner instead. And then I went for a drive. I'll spare you from my completely inadequate action content filming skills and quickly summarize how the roughly 100 kilometers of test drives went. The motor does not have enough torque to get going from a standstill. The maximum speed is faster than I can pedal. The motor heats up quite a bit when using it for long periods of time because I had to set something crazy like 60 amps as the maximum current to get enough torque from the motor. Any uphill grade larger than about 2% would stall the motor without power input from the rider. And all the added extra weight makes the ride quite uncomfortable. Especially on these forest trails. Yeah, this bike is definitely outside of its comfort zone. In short, the motor would probably have been useful somewhere with completely flat terrain. But here where I live, it was garbage. So, is that it? Do I admit defeat and say that I cannot design a useful motor? You wish. Can't break me that easily. Watchers of my previous video will recognize what this is. See, I originally wanted to make a motor with electrical steel cores in the stator, but due to some engineering mistakes, I made a compromise and made an air core stator instead. The problem with the electrical steel stator was that the strong neodymium magnets on the rotors were so powerful that the rotor got pulled into contact with the stator, because the chassis of the motor was not rigid enough. So that is the problem I should have solved instead of compromising on the core design. Now, the solution might seem obvious at first. Just use some lightweight and non-ferromagnetic metal. Like aluminium. However, unfortunately, the motor design isn't perfect and there is some magnetic flux leakage from the back irons. That means that if I were to use metal, there would be eddy currents generated in it, which would be quite a significant inefficiency. So, what do? Carbon fiber. I did some simulations in FreeCAD and found that 5mm of even poor quality carbon fiber reinforced polymer should be sufficient for my needs. I am lucky that I have a CNC router as well as a shop vacuum with an M-class filter and adequate PPE, as anything less makes cutting carbon fiber on a CNC potentially quite hazardous for health, due to all the airborne needle-like carbon fiber dust particles that get produced while cutting. Now, if you want to use carbon fiber in your projects but don't have the necessary equipment to do so, then did you know that in addition to making PCBs, our today's sponsor PCBWay also offers CNC machining services? For example, I can export my part made in FreeCAD as a step file. Then, by going on PCBWay.com and uploading the step file, defining the quantity, material, and any other requirements like surface finish, and then submitting the part for review, I could have the part at my doorstep in just a couple of days. It really can't get much easier to have access to CNC machining services. But now, back to the video. Before I could rebuild the electric motor, I had to first disassemble the almost useless air core motor. And immediately I came across an issue. The expansion sleeve seemed to have developed some attachment issues to the shaft. It took a lot of leverage and percussive persuasion to get it off. And once I did, I could immediately spot the problem. Somehow, a piece of a burr or something had completely scored the shaft and the sleeve. If anyone has any ideas on how that could have happened, then I'm all ears. I also noticed that one of the bearings had somehow gotten damaged. I don't really know how this happened either. I also reworked the motor design ever so slightly and managed to add in a thrust bearing into the design, which should spread out the humongous stator-rotor magnetic attractive force more evenly. After all of these quick and relatively easy to implement changes, I just simply had to reassemble the motor. This time, with the upgrades, the rotor did indeed stay well clear of the stator. So I hooked it up to the VESC, reran the setup, and... now that is torque. This motor is now working much more like how I originally envisioned it. However, something you might notice here is that it seems to have trouble starting up. The reason for it is that the Hall effect sensors on the stator don't seem to work properly. Lucky for me, the VESC motor controllers also have something called high frequency injection capability. Honestly, I don't really know how HFI works, but by adjusting some voltages, it's possible to get nearly as good low-speed performance as with Hall effect sensors. So, instead of replacing the Hall effect sensors, I tried HFI instead. Installing the refurbished motor was obviously more or less just a drop-in replacement and went without a hitch. I also made myself an anti-spark loop key. The anti-spark connector used in this prevents high inrush currents when connecting up the battery, which you can often hear as a kind of plop when plugging in the battery. This inrush current would damage the capacitors in the motor controller over time, as well as degrade the connector itself. The loop part of this device means that I can immediately kill power to the bike by just pulling out the loop key. And the key part, well, it kind of acts like a very easy to bypass key. Before long, my e-bike was once again ready for a ride. This time with a little bit better action camera footage. Now, I must come clean. I haven't actually, this isn't right after the previous clip. I have been driving this bike for like 50 kilometers by now. Basically because the tensioner, the loop key, the Bluetooth, those are things that I kind of figured out that I needed only after I had driven it a little bit. I still need to give ever so slight, push at the beginning,
but it's definitely a lot better than it was before. So I mean, I can kind of demonstrate it. So oh no, it gets going this time. Ha! There we go. So seems like I don't even actually need any power put in by myself. So to start with, the bike is still pretty loud. Oh wow, it's a DIY bike. Now we are coming up on the climb where previously this bike was with the previous motor. It was completely incapable of doing it. This motor, I do have to put in a little bit of force here. Last time I was already on the roadside here, so clearly an improvement. There we go, no need to stop. Last time I had to push the bike up this. This time, while I do have to put in a bit of power, you know, I don't have to walk the bike up the hill. Let's see for a moment. It's not that warm. Just by feeling, not that hot, not that warm.
Well, past me, I got to use my friend's thermal camera to give a little bit of weight to this subjective thermals feeling of the motor. After about 100-meter height gain on an average grade of about 5.5%, the motor was still just lukewarm. So, I could actually push the motor way harder and way longer if I wanted to.
Now, something that this motor has some trouble with is actually its maximum speed. Right now, with these two batteries in series, and well, it's two series, two in parallel, it's 40 volts. I mean, right now you can see it's actually like 55% full, but that's whatever. And you'll see that the maximum speed is only like 19-20 kilometers an hour, which is fine. I mean, here in Europe, 25 kilometers an hour is the maximum that you're sort of allowed to have, but maybe I would put actually 3 in series to get 60 volts and therefore close to 30 kilometers an hour as the max speed. Yeah, I will demonstrate the maximum speed now. I mean, I have to pedal, so you'll see me pedaling, maybe, I don't know. But know that I am not actually putting in any power. It's all the motor is doing that's gonna be happening here, and this is uphill, so alright, yeah. So seems like right now it got only up to 18 kilometers an hour. That's because the battery is, you know, half flat already. But full charge it'll go up to 20 kilometers an hour. So yeah, the speed not the best. The acceleration though, I'll do an acceleration test again. The acceleration I think is pretty good. Let's check again. I mean, the very low end torque is maybe not that great, but that's probably mostly because of the Hall effect sensor problem. I have to use HFI, and the battery is a little bit flat. Alright, I'm gonna spend some time riding the bike now, I suppose.
I kept riding the bike. I expected something to go wrong. The chain to snap, the tensioner to fold in half, the motor to explode or break off the bike frame after a big bump in the road, the batteries to burst into flames, or the motor controller to overheat from an improperly made motor or something. But nothing happened. The e-bike just kept working, kilometer after kilometer, day after day. So, I think I did it. If I was asked whether I had made a useful electric motor and consequently a useful e-bike while I was still using the first version of this motor, I would have had to conclude that it was severely limited in usefulness, at least for where I live. But the upgraded, fixed version, while it is a pile of jank, it's genuinely on par with low-power hub motors on the market. Exactly what I designed it for. The motor is useful. The e-bike is useful. At this point, I must thank you for watching, and as always, until the next time, stay curious. Being able to bike around these parts more easily may have also sparked in me a small itch for mountain biking. Oh dear.